Okay, well, thank you very much for coming again and again. I would like to thank Ishan, who has made it a very enjoyable time here. He even very kindly arranged a tennis match for me yesterday. Unfortunately, he didn't arrange that I would win, but nevertheless, it was fun playing. Well, I want today to talk about plumes. Oh, and the other thing I think I've noticed, and I've had this feeling a long time before, an hour and a half is a very long time for the audience to concentrate, and most important for the lecturer to concentrate. So what I'd like to do with Ishan's agreement is after 40-45 minutes, we just have a 5-minute break where you can just stretch, talk to each other, do whatever you like. Is that okay? Right, good. Plumes, right. So here's a typical plume. There's been hot air somehow or other released from what's below this picture, and it doesn't matter what it is. It goes up into the lighter, it goes into the heavier air. It's hot, and so it is light. There's some vapor that gives it the color, but that's irrelevant. What is just relevant is the fact that this is less dense than here, and so it rises. And just an aside, if you don't mind my saying, people sometimes say it rises up. It's impossible. It can't rise down, so you just say it rises. So it rises. You can't see, but you will see soon that, and you can imagine from this photograph that it's turbulent. It mixes in with the environment, and it becomes larger in horizontal length scale as it goes up. Here's now an example of a plume in the laboratory. It's dyed red. It's less dense than the environment, and you can see here more clearly how it grows in horizontal scale as it goes up. And here again, you can imagine it's turbulent. Now, I want to do an experiment for you, but I'm extremely nervous because I've never done this before, and especially I've just been given this a few days, that'll be the day, a few minutes ago, and I hope it'll work well. If it doesn't, throw me out. What I'm going to do is to make some rather heavy fluid here. I'll tell you what, we'll add 2. This is done very carefully. Sorry? You can try brown sugar for the color. Thank you for the advice. There's a mixture of grains here now, so this is... Now, I was thinking of using this red ink, but I think Ishan's idea is much better. We'll hope it's all right. You know what, Ishan, I'm going to add a bit of red dye. And I'm going to make a bit of a mess, but... Now what we're going to do, because I can't get it in the same geometry, but under the Boussinesq approximation it makes no difference, I'm going to add heavy water. You know it's heavy because of the sugar, and see what it's like. Now can you see it from there? I asked someone in the back and they said I don't have to view it, but let's have another one. Should I put a white background? Okay, does somebody have some paper? You didn't see it as well as it might? I mean, I could... Now, the proof that it's heavy, in case you don't believe me, is it all came to the bottom. Yeah, I'm not trying to cheat you in any way. Okay? Now, it's of course not as good as this, but it's the real thing. Ah, yeah. We talked about the cricket. And I saw this. India versus Australia coming to Adelaide. The first series opens tomorrow. Yes. Then I looked down a little more, and you know what I found? Now, I'll tell you what, I'll start you off. I recognize this guy. Who are the others? Can you do it? But now, it's not funny. Not at all. Because when the last time we talked about the cricket, you remember I said in very Australian determined effort, we're going to win. Ishan said, no, you're not. And so I placed a bet with him. You remember that? Which he accepted. That's illegal for cricketers to accept bets on their team. So it's not funny. And Australia's going to win anyhow. Yes. Okay. Now, I'll show you some examples of plumes in the natural world. This is now a photo of the eruption. I can never remember how to pronounce it. Even when it's written there, I can't pronounce it. So I just call it E. This is the eruption of E in Iceland in 2010, which caused such enormous troubles. And you see again a plume that you can imagine is turbulent, as you saw here, horizontal scale increasing, and then what you just begin to see here is that the wind is playing a role, and we'll talk some more about that later. And you see the heart of the volcano. It's really hot down there. There's quite a bit of fire going on. This is now another example of a volcanic plume. I think this is Mount St. Helens, but it doesn't matter where it is. But the point I want to make here is that all these turbulent plumes really rest on the foundation that the input velocity has to be linearly related via a coefficient that's generally written as alpha times the vertical velocity. Alpha is about 0.1, and this is known as Morton, Taylor, and Turner. They wrote a paper, and here they are, Morton, Taylor, and Turner. Morton came from New Zealand. He was a really wonderful character, a great friend of Edmund Hillary's, the climber. And he twice saved Edmund Hillary's life. They were practicing climbing in Austria, and Hillary went off a little far-fetched on a ridge which Morton was sure was going to collapse. And so he dug his ice axe into the ground and made a firm stance, and sure enough it did collapse. And more or less the same thing happened the second time. Hillary must have just thought Morton was terrific. G.I. Taylor, the famous fluid dynamicist of whom it was said he had a hotline to God. God would tell him what to do. And Stuart Turner, the wonderful laboratory experimentalist who was a great mentor to me. And the point here is that Taylor was asked during World War II what difference it would make if you had a fire which cleared the air on the English airports, if you had one big fire that was meant to lift the air and clear it so the planes could land, or if you had the same amount of wood, because they were burning wood in those days, to hell with climate change, you had the same amount of wood but distributed around the airfield. And that was a very important question, and it turned out there's no difference at all once the plumes connect with each other. And that was Taylor's contribution. They expand, they connect with each other, and then it really doesn't make much difference. He worked on that as a rather secret piece of investigation during the war, wrote a confidential memo about it. And then George Bachelor, totally independently, when he was awarded a prize from the British Meteorological Society, wondered about plumes. Maybe he'd talked to GI, I don't know, and made that discussion or that statement that the horizontal velocity has to be related to the vertical velocity linearly, and he saw two things immediately. One is that the coefficient alpha couldn't be calculated. He just how he saw it, I don't know. And only now we're just beginning to make calculations. But he saw that, and so he said, I know, we'll get Stuart Turner to do experiments for his PhD in the laboratory measuring alpha. And I'll show you how that's done in a minute. And having a value for alpha, we'll then get Bruce Morton to finish off the theory, which I'll explain to you in a minute, use that value of alpha and make some predictions. And I'll keep you all on tenterhooks. Let's see how good it is. But I will show you that. Oh, and so here's George Bachelor. Gee, you can hardly see this. He was a wonderful guy, great fluid dynamicist. I'm sure you know him from his books. He had the insight, and in my opinion, his name ought to be associated with it, because he set the two students to work. And when they'd finished it and were publishing it, in fact, I'd already written the manuscript due, I said, but I had a confidential manuscript on that 20 years, well, it wouldn't have been 20, this was in 1956, so 10 years ago, 15 years ago, and he insisted, according to both Morton and Turner, having his name on it, whereas I think it was George who had, after the effect, maybe the insight that there was a linear relationship. Okay, some more smokers. This is at about 2 kilometers depth. At the bottom of the ocean, but at where there are ridges. And what happens is that down here there's large amounts of liquid rock, hot liquid rock, magma. Water at oceanographic temperatures seeps through down a depth, and it melts because it's warmed up some of the minerals at depth that have a lot of sulfides. But then there's convection, just as we talked about yesterday. It gets lighter because it's heated. It's taken out some of the sulfides. It comes up here to the top of these sort of crystal piles or rock piles, and then it gets cooled enormously by the seawater and it deposits its sulfides. And that's why they're black, because these are all a lot of little, very minute crystals. Now, there are two things that are remarkable about this. First of all, the first people who found it, everybody agrees with this, were members of an Alvin cruise. Alvin is a little submersible that's run by Woods Hole. It takes a captain who steers the boat and two scientists. They're all squashed up, and they spend hours and hours on this Alvin with the captain crewing them around and the two scientists. I've occasionally asked, what happened, because we're all squashed up, what happens if you want to relax? Shall we put it that way? No one's ever answered me what happens there, but I'm sure they work it out somehow. Anyhow, two scientists and one captain. And I've spoken to 6 people who said they were on the first cruise that discovered these black smokers. I said to the 3rd, 4th and 5th. So I don't know what the truth is. But what is fascinating, what they already glimpsed at, but later scientists found out, is that here at the bottom of the ocean, so we're about 2 kilometers deep here, no sunshine whatsoever. There's a gigantic marine community. There's life living 2 kilometers down without any sunshine. Now, that was thought to be absolutely impossible, but the reason is that the sulfides here, because they're heavy, they fall out of this cloud, and instead of living on sunshine, so to speak, they live on those sulfides. And there's meant to be fabulous fishing and everything there. No one's yet, to my knowledge, used it in any way commercially, but people have written that it has great commercial prospects. This is now an eruption of a volcano, which is also unpronounceable, in Russia. You see there are lots of volcanoes here, but this day, only this one erupted. It sent a plume up here, and then the wind influenced it. And so rather than just being a plume as I indicated here, the wind came along and gave it a quite different shape. Whereas this was vertically expanding, this is expanding horizontally and going more or less at the height that the atmosphere density is equal to the density of the plume, which has particles and a different temperature. As you know, the density gets less and less as you go up. And I'm tempted sometimes to say, just to see if people would believe me, here's an indication of the scale. This is a Qantas 747, and so you see the mountain's about the same size. Now, I hope you all realise that mountain's much, much bigger than that, and I put in the Qantas flight. I could make it any size I wanted. This is now, this I can pronounce, Mount Redoubt. The famous eruption of Redoubt, and we're going to talk a lot about this. It's somewhat complicated. It's a pity. Well, it's either a pity if you want a simple example, but it's wonderful if you want to know what happens typically. What happens is there was an eruption of Redoubt in 1989, and the temperature and the particle concentration, and we'll talk much more about that next lecture, the temperature and the particle concentration was such that the plume coming out was heavier than the atmosphere at that level. And so it ran down the mountain in what's called a pyroclastic flow, or a gravity current, as we'll talk about next time. But you had this heavy, particle-laden, hot pile going down. Sorry, should I not move so much? He doesn't say anything, so I can do what I like. It dropped its particles, because while they're small particles, they're quite a lot heavier, density of about 3 grams per cc. So they drop, and at about this point here, near the end, enough particles have dropped that the density of the hot air is... he doesn't like the talk, he's going. Bye-bye. If you're all gone before the talk's over, that's okay with me, it'll save me some time. Where were we? The density of the hot air with very few particles, but still some particles rise up. Rise as a plume. Rise as a plume. Now you know that the air is stratified, that as we go up a mountain there's less and less oxygen around, the density is less, it's harder to breathe. So this plume that came up here finds itself at a level of neutral density. The hot, slightly ash-laden cloud here is at the same density as this. But it has some momentum, so it overrides that, and then it falls back and forms this intrusion. And we're going to talk about how rapidly this intrusion goes into the atmosphere. And as I'll say later, but I might as well say now, this is an interesting photograph of a volcanic intrusion, but exactly the same thing happens in lakes and in the oceans at times. You have intrusions of different density fluid, water in the oceans and lakes, and that spreads out an intrusion. It's rather easy to get a photograph in the atmosphere, damn difficult to get one in the oceans. So I can tell you they're there. People have measured them.
What is the intermediate, another stratified layer?
What is it? Good question. What's this? And that's the question, yeah? Yes. The interesting thing is nobody quite knows. It could be due to two aspects. It could be that somehow, after a while, this volcano erupted different concentration and different temperature plumes. Temperature might not have differed much, but the concentration of the plumes could have. And so where this intruded at its natural density, it could be that this is a secondary effect. It was noticed that it was later. It's also possible there were different size particles, and this particle temperature had this height as the neutral density, and this was a different particle and temperature. Exactly how it worked, one doesn't know, but it's the main one I'm going to tell you about. But that's a good question, worthwhile observing. This is now an indication of the eruption frequency, as a function of size, getting onto eruptions. And what you see is typically of Unsen. It happens, eruptions of about this size, a hundredth of a cubic kilometre, happen about once a year. And then you go to Yellowstone, which will end us all, but it only happens once every 10 to the 5th years, but it's really enormous. And these are typical examples of, you see Helens erupts once every 20 years or so, and so on and so on. And I might just say, I can't help it when I see this graph, there's a famous there's in my view, an infamous mathematician in England who's very good at spreading, I hate to say it, her views. Once got very excited, and that she said she'd looked into all terrorist attacks, and what she found is that the terrorist attacks that killed the fewest people happened the most often, and the huge number of people, like 9/11, happened most rarely, and it was almost a linear relationship, and she got very excited about this. It's obvious. You couldn't have a terrorist attack that killed the most people happening most often. That wouldn't make sense, unless you're a mathematician. Okay, now here's another little volcanic problem, just to give you some indication. There's a British Airways flight in 1985, I think it is, that was flying from London actually to New Zealand over India. It had landed once or twice, and then it was going at night, this is taken during the day, over Jakarta. Whoops, wrong one. And it was piloted by this guy, Eric Moody. The flight was called Speedbird 9. When it talked to control, it called itself Speedbird 9. And here's Eric Moody. Okay, he's flying along, it's night, he's just over Jakarta. And suddenly he notices two things quite quickly. One, all four engines have stopped. Two, this is what he sees out of his window. His first thought was, where did it teach me that in the books that I had to read and pass for my exam? And the answer was nowhere. So the captain is in exactly the same position as all of you. So I'm going to ask each one of you, here you are, that's what you see out of the window. You're the captain of the pilot of the plane, as 300 passengers or something like that, some young kids, your favourite partner, girlfriend, boyfriend, whichever you like, just to add to the difficulties. No engines, and you can't see a bloody thing. What do you do?
Jump, climb.
Sorry?
Actually climb up to see.
Jump, but sorry?
We have to climb up.
You sorry?
Dive down.
I'm sorry, I didn't hear. You go up?
You go up.
With what? One second, there are no engines and you go up. Forget this lecture. We could make a lot of money with this. Any other suggestions?
Try turning around.
Sorry?
Try turning around.
Try turning around. You turn around, it's black, 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 I'll tell you. Gee, I don't think I'm going to fly with you guys. Well, Moody had no idea from previous training, but he immediately thought there must have been a volcanic eruption. And that's why I can't see anything. And the little ash particles will have stuck in the engines and will have stopped them. So what he could have done is he could have pressed to start the engines again. There's a button there and the engines would start again. If he'd done that, I wouldn't tell you the story, because there were little ash particles that would have absolutely ruined the engine, and then he would have really been, then jumping is the correct idea. He knew what to do was to just place the plane in a slight angular glide, and he glided knowing that that would put air through the engines and clear all the particles. He was up at something like 31,000 feet. And at 1,000 feet, calm pilot that he was, he pressed the button and the engines turned on and he could fly. He then radioed Jakarta and said, look, I know I meant to fly to Melbourne, but I think I'd rather land here if you don't mind. I'll tell you what's happened. And he told them what happened. They said, yeah, sure, land in Jakarta. So he landed in Jakarta. Everybody thought he was fantastic. The passengers were enormously pleased with him. The British airline officials were enormously pleased with him. They made a great to-do for about half an hour, and then finally he said, well, thank you very much, it's very kind. He hadn't said anything for the half hour. It's very kind. I'd rather not do it again. But the passengers have all banded together, and every year on the date of the airline flight they host a dinner for him somewhere around the world, and the passengers come and he comes, and he's still alive and a fascinating guy. And there's a very interesting book written by one of the passengers telling you how terrified she was, because they apparently knew that something was going wrong. Okay, now the important point, as I've already said, and this is really the most important point of what I'm going to say today, is as the plume goes up, as it ascends, it's turbulent, it entrains air, it entrains the outer fluid, I should say, and mixes turbulently and goes up. So the entrainment is really important. That coefficient alpha, which relates the horizontal velocity to the vertical velocity, is called the entrainment coefficient. And that's how it works, and that's how it worked here. But now, let's imagine, as you know from previous lectures and from your experience in the atmosphere, that the density gets less and less and less. So the plume comes up because of its buoyancy, it mixes in, and then it comes to a area, and I've already said that, or a region, where it's the same density. But it's got some momentum now. Now it's moving. So it goes up a little further, but then it collapses and intrudes at this level. And one of the things we want to know is, what's the value of that level? Now I'm going to try and do an experiment, and this is really try because I haven't done this at all. I'd hoped to be here early enough to try it out once. But Ishan, who's dishonest and bet on the Indian cricket team, also saw to it that I didn't get here in time. What I want to do, no, I'll leave it as red. What I'm going to, yeah, thank you very much. You think it's going to work, do you? How kind of you. I'm going to make this very dense. And no more brown sugar. Okay. Now what's going to happen if I pour it in here? Sink to the bottom. Well done, all of you. It had better, hadn't it? Just right. Oh. So I have now really, though you can't see it here, but you can imagine a two-layer system. I have heavy fluid here and lighter fluid here. That's not what the atmosphere is like. It's not what this is like. As you all know, the atmosphere has a density distribution that goes down. So I'm going to have to turn this into linear density distribution. I'll do that by saying abracadabra, swirling it a little bit, rising it up. God, should have never told you that story. So now, unfortunately, none of you have a ruler to check, but this is a perfectly linear density gradient. And I'm going to see what happens Now I might use some sugar. If I put in some heavy fluid, it should be heavier than the top but lighter than the bottom.
You need some more.
Sorry?
You need some more sugar.
No, every time I've had any meal where I'm staying, I take 3 or 4. They must be wondering what I have in mind. I must have a sweet tooth. But it was Ishan who suggested the brown sugar to me. Okay, well now what's meant to happen is that this is going to overflow, I can already tell. It's still a linear gradient, perfectly linear. What's meant to happen here, oh, I don't know what's meant to happen, let's see. And I hope you can see it against the red. I'll make it as close to here as I can. I can't see anything, but can you see something? I needed some black ink. Last time they brought me some black ink. I'll try it again. Sorry? Well, was it not going down at all, or? Ah, thank you very much. Now this doesn't change the density, or it better not. Thank you. Now, as every experimentalist knows, you should never ever do an experiment for the first time. It's always a disaster. Oh, the paper, sorry. Yeah, it's working, isn't it? I'll tell you what. Lean on my luck and do another one. Oh, no. What I should do first. This won't disturb the linear gradient, of course. Oh, I'm sorry, I've got... Should I sign it as well? Oh, there's still a bit of circulation left, but that doesn't matter. It's going down. The Earth rotates, but the rotation is playing a role. But you see that it hasn't gone all the way down. It's intruded like this. Well, you know, this is a better experiment than this. I bet these guys had a bit more time. It's not my experiment. Okay, so the idea then, to continue the diagram I showed before, is we've got the ascending plume that's entraining. That's the important part of it. There's a maximum height of rise, and what is that? How big is it? And then it falls back because its momentum is used up, and it'll form an intrusion. And as I say, this can happen in lots of situations, different situations, huge range of different size plumes here. Okay, now the buoyancy frequency is an important part, and that was talked about yesterday. I'll just go over it to remind you. We have a linear density with height, just like we had in here, and we get a parcel that is here, and we lift it up an amount, and so it's now heavier than the surroundings. And because it's heavier, there's a force acting on it, and there'll be an acceleration. How much heavier is it? Well, the difference in density is going to be this distance s times d rho dz. And the higher order term, but we'll forget about that. That doesn't matter. That'll do quite well enough. Now, we've got the mass of this blob, its volume times the density, and although it's a slightly smaller density here, we don't care about that. That's the Boussinesq approximation. Mass times acceleration has got to be the force, which is the mass here times gravity, right? So we know what delta rho is, the delta rho here. So we get d2s dt squared plus n squared, where n, known as the buoyancy frequency, or as was explained yesterday, the Brand-Weisshaler frequency, which in my opinion is a terrible term, partly because there's so many damn umlauts over there, and partly because if you say somebody Brand-Weisshaler frequency, they have to think who's Brandt, who's Weisshaler. Buoyancy, then you know what it's connected with. So buoyancy frequency took over in about 1970. And this is it, n, which will come into it, and clearly that's important, telling you how high you can go. The buoyancy frequency is minus g over rho d rho dz, and really it varies all the way up in the atmosphere or in the ocean. Here's an example in the ocean, exactly the same thing. It's greater than 0 because it's stable. If it was less than 0, the whole ocean would overturn, and it doesn't do that, as you know. But there are oscillations, and then of course there is wind stresses and currents and all sorts of things, but just by itself it stays there. It's typically about 10 to the minus 2 per second. You might be able to see this is 1.5, 1, 0.5. So as n gets smaller, it gets more and more unstable, if you like, because that means that the slope is less. Here you have, because of the heating, the ocean quite stable and quite close contours, and it goes, and that means a period of order 10 minutes. So what that means is if I go to the bottom of the ocean, or to go to the middle of the ocean on a scuba dive or something, and I lift a parcel up, it'll then take 10 minutes or so to come down. It'll oscillate back and forth about 10 minutes. The atmosphere is slightly different because compressibility in the atmosphere plays a role, and I don't want to go into that, but I'll just show you the ocean example. Okay, now there are two ways really. It's 40 minutes. Let's stop here. This is a good time. 5 minutes to stretch your whatever you want to stretch, legs, arms, head, eyes, and then we'll start again in 5 minutes. Why don't we start again? And this was a good place to have a bit of a break, because now we're going to change tack a little bit. And I'm going to say we're going to analyze now these plumes and find out how high they go, how rapidly they spread, everything that we can find out about the plumes. And we can more or less do the straight plume in two different ways. One is to write down equations and solve the equations, and I'll do that for you because it's such a famous idea. The other is to use dimensional analysis. And my view is dimensional analysis is much better. And the reason that it's much better is that when I derive the equations, I'm going to make an assumption to make it easy to look at the equations. And you could say to me, but if you didn't make that assumption, what the shape is of everything within the plume, then you might get quite different results. But I can back off and say, no. By dimensional criteria, can't get quite different results. The main thing will be exactly the same, but where I'm getting 4, it might be 4.5. Or as a very famous Scottish mathematician used to say, you might be off by a factor of pi squared on 10, but who cares? So that's important, in my opinion, to do the dimensional analysis first, because that tells you what answers you have to get. Now, what are the important quantities? There's the volume of fluid that comes up, but it's the volume flux. You want to know the rate at which stuff goes out. You also want to know the buoyancy flux, because it's being driven upwards by the fact that it's less dense than the surroundings, at least where it goes out. And it must be different, at least quantitatively if it's much less dense or if it's less dense. So that must, just less dense, that must come into it. So you have the buoyancy flux, the volume flux, and G prime, the gravity multiplied by the difference in density at the bottom. Maybe I should draw it. Whoops. G prime, which is the difference in density times G over some reference density, and that's going to change as you go up, because if this is, let's say, this is not n, this is d rho dz, or rho rather. This is rho with whatever the n is. This is going to change. The difference in density between here and here is going to be different from the difference in density there.
Different density from what point?
Oh, delta rho. Sorry, I didn't make that as clear as I should have. This is the delta rho. Oh, sorry, I should. So this G prime is going to change. The rho naught is going to be the same, but what we're talking about is delta rho is the horizontal density difference.
And Herbert, why does it spread?
Oh, because of continuity. What happens is it's a turbulent plume, and it takes in fluid from here.
But how can we be certain it takes in rather than gives out? That is, what is it that...
Well, if it, by continuity, if it gave out, it would shrink.
Yeah.
But it gets bigger and bigger.
Well, why doesn't it shrink? I guess that's my question.
Ah, because basically this is still, and this is in motion.
So that relative shearing gives rise to an instability.
Gives rise to an
and that instability has a certain circulation. Okay.
And what happens, thank you for the question. What happens is that the turbulent eddies come in here, they look like that, and they take, maybe I should put that in yet another colour, they take fluid in. It's difficult for them to take fluid in, and they break the chalk all over the place, but they take fluid in.
But also they seem to push fluid out at the top of each eddy.
Oh, but the eddy comes round here, that's and engulfs fluid, and partly, well, in fact, you're asking about important details, but some details that haven't yet been worked out. But what happens is that eddy comes like this, and it takes this fluid in, because it goes like that, it brings it in. Okay. So that's how it works.
The ones on the right all have that parity.
That's right. Yeah, very important. Thanks, Jim. And sorry, that reminds me, I should say, as before, please do interrupt and ask questions.
So this part
they're really good questions. Sorry?
This part of the, before it's, I mean, in a density gradient, it goes and stops.
Yeah.
But until then, it's rather similar to a jet, right?
Yes.
Can
I just back off a little bit and I'll answer that question. First is, maybe I made a mistake in some sense about telling you of the intrusions. That's, if you like, the second part. Maybe I shouldn't have shown you the intrusion. What we're just going to talk about now is the plume part. So we're just talking about plumes, and the intrusion is important, but that's later, and maybe I should have shown you those photographs later. That's a fair point. The next is, you could have something that looks just like this, or similar to this, either because this fluid is less dense than this fluid, and so it's buoyancy that's sending it up, or it could be that you're sending it up with such high momentum, even if it's heavier than the atmosphere. If I hold a fire hose, the water, I assure you, is heavier than the atmosphere, but it will rise vertically, and that's due to a momentum driven, and the word generally is jet when it's momentum that drives it, and it's plume when it's buoyancy that drives it. And now, of course, you can immediately say, hey, it must really be both, because You know, when I squished this out, I gave it some momentum, but it was made different density by the sugar, and in fact that's true. We'll consider both of them. I'll emphasize the case where it's buoyancy, but momentum jet comes under what we're doing, except that this doesn't quite shine the light on the momentum jet. But it is important there are both of those properties there. But we're going to talk about mainly stuff that goes buoyant and rises in this plume. Now, if this was a constant density, it could rise for as long as it wanted. Because although the density will decrease, how will it decrease? Well, that's one of the things we want to calculate. In the simplest case, this has a density rho 1, and out here we have a density rho 0. It's going to engulf like this, and so this must be rho 1 minus some amount, what shall we call it, gamma, times rho 0. It's the density has got, yeah, rho 0 is less than rho 1. The density, it starts off at rho 1 and then it gets less and less as it goes up because it's taken this, sorry, I've got that the wrong way around. Rho 1 is, well, or gamma is negative. Why do you assume gamma is positive? Sorry, rho 1 plus gamma rho 0, that as it goes, oh, most important, what I should have put is gamma is a function of z, or it could be a function of z, where z is this thing up here. And it'll get, as it goes in, it's light, but it mixes in with this heavy air, and so it gets heavier and heavier as it goes up, but it'll never, in this case where there's a constant density environment, it'll never get to the same density. Doesn't matter how much it takes, it will never get to the same density, so it'll keep on going up and up. Now, part of the problem where I better make a mistake occasionally in nomenclature is I could draw this picture upside down, exactly upside down. Instead of having a light fluid going up in a turbulent plume, I could have a heavy fluid going down in a turbulent plume. So sometimes I forget whether I'm talking about a heavy fluid going down or a light fluid going up, and that's what makes me make errors here, or that's what I'm going to use. But I'll try to talk on this case. And it's made even worse, I might say, that sometimes one presents the theory in this way and then does experiments in the other way because it's exactly the same. Yeah?
So the chart you previously showed, that was between size and frequency, right?
I'm sorry, I didn't quite understand. There's a starting, well, a starting plume is what happens when it starts. I talk mainly about well-developed plumes.
That chart you have previously shown, that was between size and frequency.
That was about volcanic
So if four people talk at once, and they definitely don't, especially if it's an Indian.
That was about volcanic eruptions. It did not have to do with plumes.
No, my question is that size, what is that size, right? Is that jet or diameter of this plume?
Oh, sorry, if I've understood you, there's the question of this size here. Where does it come from? And that plays a very small role because once it's got up here, it doesn't know whether it's come from a very small space or a larger space. Is that what you were asking? Oh.
That the chart you have previously shown, that was between size and
You
some
remember the
frequency.
chart between the volcanic eruptions, the size and the frequency is, I think, that's the one.
What is meant by size? I think
Yes,
that's
sir, yes.
What's
This graph and the amount of volcanic eruption that
Yeah.
is happening. He's asking that.
so some plumes, some volcanic eruptions and some plumes can have huge buoyancy fluxes and some can have small buoyancy fluxes. Is that
what is the measure of the size of the, you know, when you said size of the volcanic eruption,
Yeah.
what is meant by size vis-a-vis
Well-
the plume geometry?
Well, it's the flux. They'll all come out of a hole that's roughly this size, and some will come with enormous rates, enormous velocities, and enormous flux, and that'll come down to the momentum flux and the buoyancy flux in which we're putting up. The momentum, well, we'll talk about this a little bit later. I'm sorry if you haven't yet got it. By the volume flux, what we mean is cubic kilometers per minute. How much cubic kilometers per minute comes out of it, because that'll make a difference. If you think about the fireman's hose, if I have the velocity higher, well, it's not the velocity that counts, it's the amount of fluid that comes out. Depending upon the size, it'll go higher. So the volume flux will play a role, and how we'll have to see. Then, because it's driven by buoyancy, G prime, the difference in gravity, effective gravity, but at the point there's a buoyancy flux here. We put a certain amount of buoyancy. We could make it much lighter or just a little bit lighter than the atmosphere, and we'll have to see how that plays a role. Does that answer the question?
Yes, sir, I got what the size you were talking about.
He got the answer.
That's okay, is it? You have to ask questions in Australian, then I'll understand. I'm sorry. But please do interrupt. Okay. Now, if it's a thermal plume, i.e. its density difference is due to temperature, just temperature, then the relationship between the density difference and the temperature difference is given by this coefficient of thermal expansion alpha, and there's a minus there because as you heat it up, it gets lighter. That makes the effective G prime this same relationship with the temperature subtracted from some atmospheric or ambient outside temperature. Now, very often, just like here when I had a sugar plume, one in the oceans has salt plumes, or one in experiment uses salt. For a reason that I've thought about for the last day or so, you always use salt in the laboratory. I've never seen sugar used before. I don't know why. Salt might be cheaper when you buy it in kilogram lots, but I don't know. But it would be the same. This could be sugar or salt. Now, because of the dimensions here, the velocity and length and buoyancy flux, you think that the velocity should go, this is the incoming velocity, should go down, or should go up with Z and go up with B in the same way. And what George Bachelor realized in this lecture is that it has to be a linear spread, because that's the only way you can get a length on both sides. So now, of course, it's not absolutely correct. There are turbulent eddies and everything here, but if I told you the details of the turbulence and everything, I'd be here forever and I wouldn't be able to do it totally. What I'm doing is I'm making an overall model which says that B, the width of the plume, B is the horizontal extent, B is a function of, and this is circularly symmetric. How do I indicate that? Goes linearly with Z. Sorry? Capital B is the buoyancy flux. So the volume flux times the initial buoyancy. So capital B will be the volume flux times G prime. Right? That's what makes it the buoy. What's happened here? I know it's my MacBook. Okay. So just by dimensional analysis, we expect the inflow velocity to go like this. We expect the radius B to vary linearly with Z. And then you saw from that plume, it's not perfect, of course, but as I said, if you want a perfect description, it's not going to work. But it is a good approximation.
So the dimensional argument assumes that the length scale at the entry is irrelevant.
Very good question. I was just about to say it, but better that you asked. What it says is that this length, this radius, what should we call it, R0, is irrelevant, because how should the plume know up here what the radius is here? 1 second. That's true. It's true here, but it's surely less true, less true, less true, less true. And when we get here, it must know. So this can't be right just at this point here. And it isn't right. I'm not making a theory. If I could make a turbulent theory that was perfectly accurate, it would be terrific. No, it would be terrible because it wouldn't describe turbulence. I'm making a theory that's useful. And some people will say, look, there's actually a virtual origin that we can bring this down here, and if we pretend the plume came out of this origin, then we can forget about this opening and just let it go up like that. But that's a detail around here. Depends, of course, how big the plume is. It could be many meters, it could be millimeters, but that's not one we're going to worry about.
I didn't quite follow why B is same as Z. I got the U is similar as.
So I didn't. Why it goes like this? Because of dimensionals.
That's fine. The next one.
Small b.
Why does small b go like Z? That was the GK Bachelor thing, because he said that's you have to have B, which has the length scale, and the only thing that has a length scale is Z. So it's got to go B goes like Z. It's got to be a cone. So that's for dimensional reasons.
So there is no other length scale.
There's no other length scale possible. And because of the dimensions of Q, the volume flux, there's got to be a relationship between Q and B that goes like this, and G prime has to decrease like Z to the minus 5/3. G prime clearly decreases because as we go here, the density difference driving the flow, that's why it's going to go slower and slower, goes down. Now let me emphasize again, this may be a little strange to you, but this is dimensional analysis, which on the one hand is very easy, on the other hand is extremely difficult because you've got to pull out the right dimensions. If I think this depends on the number of wives that Ishan has had in his life, and I make that a variable, it's going to be absolutely lousy, especially as it's dimensionless. If I want to put the time since the eruption, then I'm going to have a lot of problem. But that's not an important variable. The only important variables, and that does take some insight, are the buoyancy, the volume flux, and the buoyancy flux, though those are related. But I'm going to prove this by writing equations down, but then you'll be able to see which part of the equations are important and which part are not, because you've got this dimensional analysis. Now we've got a stratification, which we said, and that makes a difference, and we know, and that's why I discussed the intrusions eventually, it doesn't have to, but eventually it can go out as an intrusion. Well, what can this height be? Well, all it can be is proportional, now again, pi squared on 10, 5, whatever, the buoyancy factor to the quarter, the buoyancy frequency to the minus 3/4. Ishan, do you want to share it?
No, I just
Oh.
whether I got something.
You could ask me. Oh, he knows the answer better than me. You're right. Right. Okay.
H is height from the origin?
Sorry?
H is height from the virtual origin? Or
Yeah, the height h is from here. If you want to really be correct, it should be from this virtual origin, but this is really always very small. But so what that says is that the plume height, the height at which it rises in a constant n, a linear density gradient, should go like the flux here. It's used F, this is what I called B before, but this is the original from Turner's book, times the buoyancy frequency to the minus 3/4, and the 5 had just been put in here because that turns out to be the number. And Stewart, who did the experiments, you see covered this range here. So what you see is the height of rise is something like 20 centimeters. This is a tenth of a meter, and something like 20 centimeters, so something like this, 6 inches as I like to say. It worked wonderfully in his limited range that he could do experiments. You know, labs in 56 were not gigantic. Then Crawford and Leonard, who I know nothing about, did some experiments on an ice rink. And then there were some experiments done on oil fires over deserts because people wondered what would happen. And you see there's a damn good straight line, just as we'd got that this plume, I didn't write it down, H has to be proportional to the buoyancy flux to the third times n to the minus 3/4. So in some, the 5 we can never get by dimensional analysis. But this we can get just by dimensional analysis. They did more, as I'll do in a minute, Morton, Taylor and Turner, and then did laboratories, which George saw that Turner could do, and then they were extrapolated. That's not bad. That's a variation of 4 orders of magnitude. Okay, so that's not at all bad.
So my question was that we have got 3 variables, right? Q of the rho and G.
And a rho by itself doesn't play a role.
Delta rho.
Delta rho, and G, that's G prime, because it's only in terms of gravity or that it plays a role. So G prime plays a role.
So G on its own you will not say, you won't say 3 things, you only say 2.
Yeah. Yeah, and N clearly plays a role. That's the stratification there. Clearly plays a role at what its height going to be. This does not tell you what happens if it's a purely uniform ambient. Then it'll just keep on going up and up and up. Well, in that case, N is 0, and so this has to be infinite.
Naively, I could have said that Q, delta rho, and G are the 3 important parameters of the problem. But if I have got 3, I can put out a length scale.
But that's the important thing, as I said. You have to get the right parameters. And delta rho is not one of the right parameters because it's the flux, basically how quickly things are happening. G prime plays a role, but with the velocity that sends it, or the flux, which is really important. And of course the flux is related to the velocity by the area of this container. If it's going at a certain velocity and it's a bigger output nozzle, then it'll have a larger flux. Does the velocity depend, is that the important thing? No, it's the flux. It's the rate at which these things come out.
I guess to me, figuring out that it's not delta rho and G independently, but G prime, that is crucial part of the algorithm.
Yeah, that's an important part. And now, I don't know how this was first done, and it may be, to be honest with you, wrote down the equations, got the solution, and thought, well, we must be able to do this by dimensional analysis, and they did it this way. I'll tell you later on something that I've done just by dimensional analysis, where I haven't yet got the equations, but the dimensional analysis works very well because I didn't include the number of times Ishan's been married or the weight of Ishan, or because that would have had a damn mass in it. Luckily, that wasn't necessary. Yeah.
Question is about dimensional analysis. So while we have done dimensional analysis, that how do we ensure that the variable whatever we have taken are sufficient, or is there not any important variable what we have left with?
Well, if I've understood the question, that's without a doubt the toughest part of dimensional analysis. Is sort of comes out when I talk to Ishan. You have to choose the right things.
Is it iterative, or there is some procedure for it?
Is it, sorry?
Is it iterative or is there a procedure for getting
No,
the right variables?
it's not a procedure that you can work like solving differential equations, y double plus lambda squared y. It's an art. It's a very powerful art. I can't speak about India in any knowledge at all, but in Australia and in England it's not taught, though it could be taught to school kids. And it should be taught to school kids because it plays an important difference. And just an aside, let me say, when I give lectures, I frequently start a formula which I have to write down, and I have no idea properly what has to be on the right hand side, but by dimensions it's got to be, if it's feet on the left hand side, it's got to be feet on the right hand side. So don't put u cubed, because that just won't work, and I know it has to be u squared or something like that. It is very important, and what you can also use it for is to suppose that certain things are important, include it, and then show by dimensional analysis that it can't be so. So for example, if I drop this, or if I drop this, let's imagine it's a solid, I might think that the time it takes to get to the floor depends on the mass. So I'd say, well, the mass must play a role and gravity must play a role. But there's no way the time to go a height h involves mass. It's time and distance. So the conclusion must be that it will fall at a rate independent of the mass. So Newton could have worked that out, but he didn't. But of course that is Newton's law, that it's not going to depend on the mass because the force is proportional. Okay, so, and please do interrupt. It's much more interesting for me to try and describe things. So this is not bad. That's 4 orders of magnitude. Starting with 6 inches and going up 4 orders of magnitude on the assumption that alpha is a constant, that it makes no difference where you are, the vertical velocity is related to the horizontal velocity. And we'll talk about that in equations in a moment. Okay, well now I said to Andy Woods, my then 4th year undergraduate student, he then became my PhD student, why don't you work that out for volcanic eruptions and plot the height that's known of intrusions of a whole series of volcanic eruptions. We'll assume that N in the atmosphere doesn't vary much. It varies a little bit, but not very much from one bit to another. And so the important thing is the volume eruption rate. And geologists know that. And plot all the data and compare it with the theoretical curve, which was basically in existence. Use the same value of alpha, which is basically that 5, if you like. And here's the curve, the theoretical curve. And here's the volcanic eruptions. Now this is on log-log paper, or log-log slide or whatever, a log-log electronically. And you see Besimiani in 1956 is the largest eruption height in modern times. And while we can find out a lot about volcanic eruptions in prehistoric times, there's no way of finding how high it went into the atmosphere. That's beyond us. So that's the largest one, so that's 43 kilometers so. So what we're saying is that this plume idea, which I've just used dimensional analysis, and I'm going to say it's very simple, holds from 6 inches to 45 kilometers. That's not 43 kilometers. Well, it'll hold from 50, 60 kilometers, but the volume eruption rate hasn't been big enough. Not a bad extrapolation.
How in volcanic eruption they measure the volume eruption rate?
Oh, they then go along and basically know how much solid material has been put out, and then there's a bit of approximation between, if you like, the solid content which you can see on the ground and so the volume eruption rate we can work out for prehistoric eruptions, but we don't know the height. Anyhow, so that worked very well, and Andy Woods got his degree, undergraduate degree on that. Okay, now this slide, which I just stole from someone else, and in some sense I should have put in earlier, this now says we're going to begin to do a theory of an axisymmetric plume, like it's a cone, so everything is going to be independent of theta. It's just going to depend on r, the radial direction, and on z. And the really important thing is, in that case, then the volume flux is going to be the velocity multiplied by 2 pi r, because that's the area, The momentum flux is going to be u squared because the momentum is proportional to u and the flux makes it u, and again it's 2 pi rdr, and this is the, what is this? Well, this is the thermal flux. I don't know. As I say, I borrowed this slide from someone else. That's really the only thing that I wanted to show here, and I implied that before. Okay. Now let's write some equations down and prove what we've already done in a much longer way. I can't help but tell you that my eldest son, who's a very, very clever person, was given a so-called supervision in Cambridge, where that's the way undergraduates work, to come at one time to be talked to and helped for an hour by somebody rather senior. And Julian, my son, had a supervisor who we thought was incompetent. He quite frequently said to me how bad they were, and once during the supervision he said, look, I didn't understand question 6 at all, not at all, I mean not even the first line. And the supervisor said, who Julian didn't think was very good, no, it was perfect, I looked through it and it was perfect. And Julian said through gritted teeth, the first line is not even dimensionally correct. They were very embarrassed, but he'd learnt dimensions. Okay, now though we're going to write down some equations. And what we're going to say is that the velocity varies with z, or the volume varies with z, due to the input. This input has to be related to that. So it'll take in an amount, that's because velocity equals velocity, that was George Bachelor's insight, with, and here again I borrowed this, well, stolen this slide, used epsilon. So what we have is 2 pi b squared, that's the area at the height of b. The variation in that has to be related epsilon u, w is epsilon u, times 2 pi, the pi is left out on both sides, times h, which is the circle around which it comes. Or maybe another way that you could see this is to write it as the change in with ub squared is equal to, what can I remember this right now, 2u epsilon b, whoops, times dz. So that's saying over this region dz, the change in ub squared here, so this is ub squared, which is a function of z, is going to change over this dz because of the flow that's coming in here. And epsilon, the flow in is related through epsilon. Okay.
That's assuming density is constant.
No, it's saying that what happens is, this is just a volume relationship. It says the difference in volume up here, the volume flux, that's ub squared, 2 pi b squared is the radius, u is the upward velocity, that the difference between here and here has to be due to the amount that comes in. So that's the two, what am I putting the pi in? That's the epsilon b. Sorry, have I got that at that one? Oh, I left the u out, no wonder. Now I've lost the chalk. Oh, here we go. U dz, right? Epsilon u is the amount that's coming in. U is the vertical velocity. And it comes in epsilon u. And it draws it in And it does it linearly like this because this is linear, it's conical. So that's without a doubt the important thing, the so-called entrainment assumption, that the entrainment of fluid in at any layer is proportional to the vertical velocity of that layer.
And that's the answer. That's what you assume.
Yeah.
And is there any a priori reason for it to be so?
That's a good question. I'll answer it in two ways. Nowadays, that's just the assumption that works and that's right and works as I showed. What happened then, I think just on dimensional analysis, George said that's how it has to be. And that works. It is an assumption, yes, it's an assumption, but one that works very well. And well, but the point is that you have to have the vertical velocity, which has Lt to the minus 1, somehow proportional to the horizontal velocity, and it's a local effect. So it can't depend on Z, it can't depend on the initial buoyancy or the initial momentum flux, shouldn't really depend on the local buoyancy flux because it's a local business, how much fluid is being taken in. So you're quite right, it's an assumption, but it depends.
Continuity balance, right?
Sorry?
It's a continuity thing. We have taken a disk and you're saying whatever is coming in must add to what's coming.
No, I think it's important. You've raised an important point. The statement that what comes in must be taken up. That's not an assumption. That has to be true. That's the equation of continuity. But what's the ratio between what comes in and how rapidly it's going up? And if you like, I'm saying, don't understand a damn thing about the turbulent entrainment and all of this, but I'm going to assume, I think I'll use that word just because you've used it, that there's a linear relationship between these. It couldn't be a quadratic relationship because then it wouldn't work dimensionally.
Depends on,
Well, sorry?
it depends on the constant.
Well, it depends. What is not at all obvious is that the constant is going to be the same independent of whether it's a really gigantic plume or a little plume. Absolutely correct. That is definitely an assumption which has turned out to be remarkably accurate. Alpha is 0.1 and there have been a large number of experiments, all of which measure pretty much the same as alpha. Now, there'll be arguments. One guy will say, no, it's 0.95. I don't know, it's 0.095. Another will say it's 0.1. But the assumption is based on dimensional analysis, which says it's got to be locally determined,
I was wondering
and that.
whether the more or less linearity of the plume has anything to do with it being.
Oh, sure. If you imagine if you imagined that it was a quadratic plume, then you'd have something different. But it isn't a quadratic plume in a sense. That's what we, so you're right in a sense. It's an assumption, but it's an assumption driven by the data.
I agree. I guess because the entrainment is because of this turbulent entrainment which nobody seems to understand, or maybe they understand.
Yeah.
So it has. So W being equal to epsilon mu is saying something about what the entrainment must be.
Yeah, it's skating over all the details of the entrainment. And I might say this is the way it was done by Bachelor and Taylor and Willem. Nowadays, over the last maybe 3-5 years, people are looking a little more carefully. Well, they don't, the dots on the I's, in my opinion. They don't make it very much different here. This is the basis that all plume theory is on. But I'm going to say again, Ishan, you make a very good point, which in my terminology is any model building depends upon the assumptions that you put into it. And dimensional analysis depends even more, because you could bring in a whole series of other things and then it would be different. But you have to have the idea that certain things are important and certain things are not important. So you could say, gee, what about if the dropping of the ball depends on the mass of the ball? If you just say that, then it can't be there because of dimensions. But say it could also depend on the mass of me. I drop it and that plays a role. Then you'd be in real trouble, because there'd be two masses. You divide one by the other dimensionless number and that might come in, but it doesn't.
I guess what I was trying to link it to, we were talking earlier about constitutive laws for erosion.
Yeah.
This seems to be like a constitutive law for entrainment.
Yeah.
In my view of things. I'm specifying what it must be and happens to fit the data. I'm okay.
But I guess what I'm going to say, and I hope this is right, is that granular motions and intrusions are different from fluid dynamical intrusions. So yeah, so
in
it.
terms of simply model building in which there are certain equations which are constitutive in nature and some which are kinetic nature, balance laws. This seems to be of the constitutive nature.
Yeah, it is definitely dependent on the experimental evidence that it goes like a cone. Absolutely no doubt. That plays a large role. Okay, and now basically this is saying the same thing, but for the buoyancy. This is the buoyancy that's driving the motion, and we can combine these equations to get basically this set of equations. Now, if we put n equals 0, the case where it's not stratified, then we find, but now with the constants in here, that the volume flux goes like z to the 5/3. It's got to increase because you're taking more in. The momentum flux is a 10 on pi left out here. Also, but that goes like z to the 4/3. So that's writing down equations, conservation laws, but it also has some assumptions what you should put in. There's no doubt what we've said in here, as I derived over there, that the upward velocity is related to the input velocity. And that's an assumption that is, oh, and sorry, I've forgotten to say something very important, but I hope that hasn't muddled you up. What I've assumed in this model, and I'm sorry that I didn't say that, is that the velocity across the plume is uniform. I'm terribly sorry, I forgot that. That's very important, and I prepared to say that but then forgot. That we're saying that this is the velocity in the whole way. That's called the top hat profile. Now you could say, if I make measurements, is it going to be a top hat profile? No, I guarantee you it isn't. It's going to more look like this. There's going to be some variation. So that'll change the numbers, because it's a detail, but it can't change the relationships. And that's, sorry, what I had in mind when I said to you that's the advantage of the dimensional analysis, and you'll see later I'll make an assumption, and then I forgot to tell you where I was making that assumption. So the 5 that was there, that was done experimentally, that was worked out experimentally. But then Morton did some equations, and using this he sort of got the same answer. But it would be a different answer or a different number, because that 5 was got from experiments with this, than if somehow you could do it with that. So the numbers will be different, but the dimensions will not be different. And as you saw, the relationship between 6 inches and 43 kilometers goes appropriately like z to the 5/3 or something. And if it turns out that really it should have been 2 as a prefactor rather than the 1 that I used, over such an enormous range and that it goes like z to the 5/3 or whatever, that beats anything, and the prefactor doesn't matter that much. Oh, that's 5:30. I think we'll leave it at that. There are enough puzzled faces in the audience that I'll leave it at that. And we'll talk some more about this next time. Yeah, tomorrow I'm talking about something totally different. I've sent Ishan an abstract, but the abstract basically says mathematicians love getting similarity solutions. I simplified solutions. When does a real solution look like a similarity solution? Maybe it's never, and there'll be some times when it's never, and I'll tell you about them. Maybe it's a few seconds. Maybe it's hundreds of years. I'm a geologist, so a flick like this is a few 100,000 years. We'd better work that out.
Have any questions?
Okay, well, thank you very much.